So the third and final part of the cyclic barrier discussion will have us walk through another variant of that example application that runs all the GCD algorithms simultaneously in different threads, except this time we're going to use cyclic barriers as opposed to countdown latches. So same approach, same four algorithms, same behaviors, not important. Let's take a look at the code. So this has a lot of things in common, but it's going to have a couple major differences because we're using cyclic barriers as opposed to countdown latches. But you can see the code here to get the feeling for how it works. So we've got the entry point into the unit test. We make the list of GCD tuples, which implement all the different algorithms. We create the entry barrier, and you'll notice that we make the entry barrier be the number of tests we want to run plus 1 for the thread that's initializing the test. So we don't want anything to run until everybody's ready to go. So we give it the number of tests plus 1, and you'll see why we do that. We also give it a barrier action that's going to reinitialize the input on each iteration. We then go ahead and create an exit barrier, which also is the number of tests to run plus 1 for the main thread that initializes everything and kicks it off. We're now going to go through n cycles. So let's say we are going to run this 10 times just for fun to see. And the reason we're going to run it for 10 times is we want to see if it's always the case that the Euclid algorithms outperform the big integer GCD and the binary GCD implementation. So we're going to run this test multiple times. Every time through the test, we're going to create a new thread. This will run the GCD cyclic barrier worker class, which we'll look at in a second, passing in the entry and exit barriers. And we start the threads. We don't want anything to start yet. And moreover, we're actually going to make everybody wait until everybody's ready. This is what was different from the countdown latch example, where the countdown latch example just said, all right, as long as a thread starts to run after the await was called on, or the countdown was called on the entry barrier for the countdown latch, it's fair game to start running. But it didn't ensure all the threads started running at the same time. Whereas this approach is going to make everybody wait until they're all up and running and ready to go. So we would expect the timing comparisons to be more accurate here because things really are all going to start running at the same time. We then, after we let everybody start to run, we then wait for everybody to finish. And you'll see here that after await returns for the cyclic barrier, its count is automatically reset back to the total number of parties. So we don't have to make a new instance. This, again, is different from the countdown latch. The countdown latch didn't have this capability, whereas the cyclic barrier does. So let's take a look at the actual cyclic barrier worker class. It implements runnable, so it can run in a thread. It stashes away the entry and exit barriers in local fields in the instance of the class. And its run method looks almost identical to what we had before, a little tiny different, but its behavior is somewhat different. So this is the run hook method that gets called after the thread is started. We call await, and this call will block until everybody else has called await. So what that means is that when the final thread calls await, at that point they all start to run at the same time, whereas before things could sort of show up in different orders and they wouldn't be forced to wait. So this fixes the limitation we had with the countdown latch. We then go ahead and run the test, don't care what it does, and then the last thing we do on the way out is we say, we're finished, and once again, everybody has to wait until everybody's reached the end. So this is an entry barrier that waits, that's an exit barrier that makes all the threads wait, and because it's a cyclic barrier, we can run this test over and over and over again for each of those n cycles, and it'll keep resetting itself automatically every time. Okay, so that's the end of the cyclic barrier example.